Welcome to Biology Access. In today's class, we're going to do the continuation of population ecology. So we're going to look at the second type of growth model, which is logistic growth model. Now, logistic growth model is actually different from exponential growth model. In exponential growth model, it's assumed that there is no limited capacity, there is unlimited resources, available shelter, and all that. But in logistic growth model, it is assumed that the environment is carrying capacity. That means the population at which the environment becomes, at which the resources of the environment can sustain. Beyond that, there will now be inadequate resources. So in logistic growth model, we have a situation whereby the population starts by increasing gradually, followed by a period of rapid growth. And when it's getting close to the carrying capacity of the environment, it now slow down. It can't go beyond. Once it goes above, a little bit above the carrying capacity, you have to go down, because environment has a way of regulating population. Unlike the exponential growth model, where you have the assumption that there is no limiting factor and the population is growing without restriction. All right. So we're going to look at the formula for logistic growth model. Is similar, but in this case, you have to impute the carrying capacity of the environment into it. As you all know, this is the growth rate. This is the population size. This is the carrying capacity, and this is also the carrying capacity. So this formula is the same thing as this. It's just a mathematical variation of it. This is change the population. So we can eventually attempt a question regarding logistic growth model, the way we did for exponential growth model. So assuming that a grasshopper population is growing according to logistic equation, if the carrying capacity K is 1,000 grasshopper and growth rate is 0.2 individual per month, all right? What is the maximum possible growth rate for the population, all right? So as usual, we are going to use our equation. Either this or this will give you the same answer. But take note, in this equation, you are given R, which is 0.2. You are given carrying capacity, which is 1,000, but population size was not given. You can easily get that so that you can get your the maximum possible growth rate. Now, the population size at which the maximum possible growth rate occur is this, the middle. That's the middle of the carrying capacity of the environment. So that's the reason why I wrote here. First, you have to get the population size by which the maximum growth rate actually occur or is possible. So, and that population size is actually gotten where you have n equals to k all over 2. You can see in this place, at half the carrying capacity, the population is growing exponentially. That's where we actually have the maximum growth rate happening. So you have the population size at this place being where the maximum possible growth rate actually happen. So in this case, we now have n. The population size is k, which is carrying capacity all over 2, 1,000 all over 2, which is 500. So when the population is actually 500, that's where the maximum growth rate actually occur. And you can notice that it will be around this region where the population is growing exponentially. In this region, population there is maximum possible growth rate. All right. So we now impute that into the equation. This is the equation as usual. R is 0.2 times, we multiply n, which is 500. K is 1,000 minus n is 500 all over 1,000. So if you subtract this, you have 500 all over 1,000. Now, if you divide this, you have 0.5. So now have 0.2 times 500 times this. And this is actually the maximum possible growth rate for the population. So that means in a month, the maximum that can be added is actually 50 individuals. All right. So please, it's a very simple method. There are other variations. Any method which the question is given, the other, you can also answer it. Now, you can also take this as an assignment. Assignment 2. A fishery biology is maximizing her what? Fishing what? Yield by maintaining a population of a lake catfish at exactly 500 individuals. Predict the what? Instantaneous population what? Growth rate. If the population is stuck with an additional what? 800 catfish. In this case, assuming that arrow, the growth rate for the population is what? This. So you can attempt this question is direct. And other questions, send any questions that you feel that you have challenge with. Your answers will be provided. Thank you for listening, and if you have any other question, you can drop in the comment section or send a mail.